Hello and welcome to Computing Fundamentals 2. In this video, we are going to have a closer look at graphs connectivity, paths, connectedness in directed graphs, vertex connectivity and edge connectivity, and also we will discuss connectedness in direct graphs, paths and isomorphism. Finally, we will discuss a technique for counting paths between vertices. Many problems can be modeled with paths formed by traveling along the edges of graphs. For instance, the problem of determining whether a message can be sent between two computers using intermediate links can be studied with a graph model. Problems of efficiently planning routes for mail delivery, diagnosis in computer network, and so on can be solved using models that involve paths in graphs. Informally, a path is a sequence of edges that begins at a vertex of a graph and travels from a vertex to vertex along edges of the graph. As the path travels along its edges, it visits the vertices along this path, that is, the endpoints of these edges. So let us discuss the formal definition of paths. Let n be a non-negative integer and g an undirected graph of path A with length n, which goes from u to v in G as a sequence of n edges e sub 1 up to e sub n of G, for which there exists a sequence where x0 equal u, x1, xn minus 1, xn equal v of vertices, such that e has the value of I equal to 1 up to n, and the endpoints will be x sub I minus 1 and x of I. Based on this definition, we have the following facts about paths. When the graph is simple, we denote this path by its vertex sequence. The path is a circuit if it begins and ends at the same vertex, let's say u equal v, and has a length greater than 0, so it is not a loop. The path or a circuit is said to pass through the vertices x1, x2, xn minus 1 and traverse the edges e1 up to en. A path or a circuit is simple if it does not contain the same edge more than once. So in the simple graph shown in figure 1, A, B, C, F and E are simple paths of length 4, because the edges A and D, D and C and F and E. However, D, E, C, A is not a path, because E and C is not an edge. Note that B, C, F, E and B is a circuit of length 4 because the edges B and C, C and F, F and E and B are edges, and this path begins and ends at B. The path A, B, E, D, A, B, which is of length 5, is not simple because it contains the edges A and B twice. Many social scientists have concluded that almost every pair of people in the world are linked by a small chain of people, perhaps containing just 5 or fewer people. This would mean that almost every pair of vertices in a friendship graph containing all people in the world is linked by a path of length not exceeding 4. When does a computer network have the property that every pair of computers can share information if messages can be sent through one or more intermediate computers? When a graph is used to represent this computer network where vertices represent the computers and edges represent the communication links. This question becomes, when is there always a path between two vertices in the graph? Now let us take a definition to explain what we mean by connected and disconnected graph. An undirected graph is called connected if there is a path between every pair of distinct vertices of the graph. We say that we disconnect a graph when we remove vertices or edges, or both, to produce a disconnected subgraph. Thus, any two computers in the network can communicate if and only if the graph of this network is connected. Now we will discuss the graphs shown in figure 4. Graph G1 in figure 4 is connected because for every pair of distinct vertices there is a path between them, and you can verify this. However, the graph G2 in figure 4 is not connected. For instance, there is no path in G2 between vertices A and B. So this leads us to conclude the following theorem. There is a simple path between every pair of distinct vertices of a connected and directed graph. So let us take one more definition to understand the meaning of connected graphs. A connected component of a graph G is a connected subgraph of G that is not a proper subgraph of another connected subgraph of G. So a graph G that is not connected and two or more connected components that are disjoint have G as their union. So we will have now an example. The graph H shown in figure 5 is the union of three disjoint subgraphs H1, H2, and H3, none of which are proper subgraphs of a larger connected subgraph of G. These three subgraphs are connected components of H. This may lead us to ask the following questions. How connected is a graph? Suppose that a graph represents a computer network. Knowing that this graph is connected tells us that any two computers on the network can communicate. However, we would also like to understand how reliable this network is. For instance, is it still be possible for all computers to communicate after a router or a communication link fails? To answer this and similar questions, we now develop some new concepts. Sometimes the removal from a graph of vertex and all incident edges produces a subgraph with more connected components. Such vertices are called acute vertices. The removal of acute vertex from a connected graph produces a subgraph that is not connected. By definition, an edge whose removal produces a graph with more connected components than in the original graph is called acute edge. Note that in a graph representing a computer network, acute vertex and acute edge represent an essential router and an essential link that cannot fail for all computers to be able to communicate. To understand acute vertices and acute edges, we will discuss the following example. Find the acute vertices and acute edges in a graph G1 shown in figure 6. The acute vertices of G1 are B, C, and E. The removal of one of these vertices and its adjacent edges disconnects the graph. The acute edges are A and B, C and E because the edges A and B is incident to A and B, and also the edges C and E is incident to C and E. Removing either one of these edges disconnects G1. There are two notions of connectedness in direct graphs, depending on whether the directions of an edge are considered. A direct graph is strongly connected if there is a path from A to B and from B to A whenever A and B are vertices in the graph. For a directed graph to be strongly connected, there must be a sequence of directed edges from any vertex in the graph to any other vertex. A directed graph can fail to be strongly connected but still be in one piece. Definition 3 makes this notion precise. A directed graph is weakly connected if there is a path between every two vertices in the underlying undirected graph. That is, a directed graph is weakly connected if and only if there is always a path between two vertices when the directions of the edges are disregarded. Clearly, any strongly connected directed graph is also a weakly connected. So let us take an example to distinguish between strongly weakly connected graphs. Are the directed graphs G and H shown in figure 7 strongly connected? Are they weakly connected? So G is strongly connected because there is a path between any two vertices in this directed graph. Remember, G is also weakly connected. The graph H is not strongly connected. There is no direct path from A to B in this graph. However, H is weakly connected because there is a path between any two vertices in the underlying undirected graph of H. There are several ways that paths and circuits can help determining whether two graphs are isomorphic. For example, the existence of a simple circuit of a particular length is a useful invariant that can be used to show that two graphs are not isomorphic. In addition, paths can be used to construct mappings that may be isomorphism. As we mentioned, a useful isomorphic invariant for simple graphs is the existence of a simple circuit of length k, where k is a positive integer greater than 2. So let us take an example that shows how we can use paths to identify isomorphism of graphs. Determine whether the graphs G and H shown in figure 8 are isomorphic. Both G and H have 6 vertices and 8 edges. Each has 4 vertices of degree 3 and 2 vertices of degree 2. So the three invariants, the number of vertices, number of edges, and degrees of vertices all agree for the two graphs. However, H has a simple circuit of length 3, namely V1, V2, V6, and V1, whereas G has no simple circuit of length 3, as can be determined by inspection. All simple circuits in G have length at least 4. Because the existence of a simple circuit of length 3 is an isomorphic invariant, G and H are not isomorphic. So we will discuss another example. Determine whether the graphs G and H shown in figure 9 are isomorphic. Both G and H have 5 vertices and 6 edges. Both have 2 vertices of degree 3 and 3 vertices of degree 2. And both have a simple circuit of length 3, a simple circuit of length 4, and a simple circuit of length 5. Because all these isomorphic invariants agree, G and H may be isomorphic. So we need to study this case further. To find a possible isomorphism, we can follow paths that go through all vertices so that the corresponding vertices in the two graphs have the same degree. For example, the paths U1, U4, U3, U2, U5 in G, and V3, V2, V1, V5, V4 in H. Both go through every vertex in the graph. Start at a vertex of degree 3, then you go to a vertices of degree 2, 3, and 2 respectively, and end at a vertex of degree 2. By following these paths through the graphs, we define the mapping of the function f, where f of u1 equal v3, f of u4 equal v2, and f of u3 equal to v1, and f of u2 equal v5, and f of u5 equal v4. So G and H are isomorphic, either by showing that f, the function f, preserves edges, or by showing that the appropriate ordering of vertices, the adjacency matrix of G and H, are the same. So the number of paths between two vertices in a graph can be determined using its adjacency matrix. And this is basically another theorem for us to understand. Let G be a graph with adjacency matrix A with respect to the ordering V1, V2, Vn of the vertices of the graph with directed or undirected edges, or with multiple edges and loops allowed. The number of different paths of the length r from v of I to v of j, where r is a positive integer, equals the entry at row I, column j of a to the power r. To understand this theorem, let us take an example. How many paths of length 4 are there from A to D in the symbolic graph G in figure 11? The adjacency matrix of G ordering the vertices as A, B, C, D is shown at the figure. The number of paths of length 4 from A to D is the entry at row 1, column 4 of the matrix A to the power 4. So we have to do a matrix multiplication here first in order to find A to the power 4. Because here are exactly 8 paths of length 4 from A to D. By inspection of the graph, we see that there are 8 paths of length 4 as listed in the slide. So we name 1 or 2 of them. The path A, then B, then A, then B, then D. Also, we can go from A to C, then to A, then to B, and then to D. So in this video, we discuss graphs, connectivity, and paths, connectedness in undirected graph and directed graph, paths and isomorphism, and then we discuss counting paths between vertices. In next video, we are going to discuss a very important problem, which is Euler circuit and Hamilton circuit.